The last two examples that I will show you are examples for spherical coordinate transformation in spherical coordinate. In 14.8, you will learn Jacobian in a much bigger and general form. At this point, what we will do, we will just remember that when we change from the Cartesian, rectangular Cartesian system to the spherical coordinate system, our integration from the region with respect to dx, dy, dz has become integration over the region with respect to d rho, d theta, d phi. And what we will remember, we're always going to multiply by rho squared sine phi. This thing, when we change to polar or to the cylindrical coordinate system, we have the Jacobian value of r. The Jacobian value of r, the spherical interchange is going to be rho squared sine phi, d rho, d theta, d phi. And this is something that we will remember now. In the next section, we will clear up this concept a little bit more. So what we are doing here in this problem, we are using the spherical coordinates to find the mass of the sphere, x squared plus y squared plus z squared equal to a squared, with the given density k. The density at any point is proportional to the distance of the point from the z-axis. So remember, any point will have a distance from the z-axis. So distance from the z-axis for any point is always given by square root of x squared plus y squared. So this is my first objective. Then I'm going to remind myself what are the spherical coordinates. X is going to be rho times cosine of theta sine of phi. Y is equal to rho times sine of theta times sine of phi. And z is equal to rho times cosine of phi. Also, we will talk about the other interchange. Rho is equal to square root of x squared plus y squared plus z squared. This is going to help us understand the relationship between rho and x, y, z coordinates, also the limits of rho, so to say. And then your theta is going to be the arc tangent, just like polar coordinates, y over x. And finally, the phi value is going to be arc tangent of z over r. So these are your interchange information. So now think about square root of x squared plus y squared, the distance from z-axis. It will become square root of rho squared, and then you will have cosine squared theta times sine squared phi plus rho squared sine squared theta times sine squared phi. You can factor out the rho squared sine squared phi, and that will become rho squared sine squared phi times cosine squared theta plus sine squared theta. So that is 1. So I will go ahead and say that this is rho sine of phi. So what this problem has told you, that the density, the rho xy function, so rho, this time I'm going to write it as the continuous density, rho. This thing, according to the problem, is proportional to the distance from the z-axis. So proportional to rho sine of phi. Which implies what? Which implies the density is equal to a constant k times rho sine phi. And that's pretty much what we wanted to know. And now we're going to set up the integration for finding the mass. So we're finding the mass, and the mass is going to be integration. Remember the limits. So the limits for your value of theta is between 0 and pi, and that's something that we know from the spherical coordinate system. The values are always between 0 and pi. Phi, whereas, is between 0 and 2 pi. And r is the radius of this sphere. And remember, my sphere is a sphere of radius a units. I have said x squared plus y squared plus z squared equal to a squared. So I'm going to go ahead and say that the value of r is bounded between 0 and a. So this is the integration. Let's first do the integration with respect to r. So we'll say 0 to a rho sine phi is the density function times rho square sine phi. Do not forget, this thing is going to come every single time we do the substitution of spherical coordinates from rectangular coordinates. And then as I'm doing it with respect to rho first, I will say d rho, and then say I'm doing the antiderivative with respect to theta. So we'll say d theta, and limits of theta are 0 to pi. So what I'm going to do for a change, I will integrate from 0 to pi over 2, and I will multiply by 2. That will take care of the integration between 0 to pi. And finally, the limits for phi is between 0 to 2 pi, and I'm again going to do the same thing. I will integrate between 0 to pi over 2 and multiply 4. All right, so what it is going to give us is d phi as the last integration variable. So let's try to simplify and start antiderivative. So 8 times integration 0 to pi over 2, integration 0 to pi over 2, and you are doing the integration with respect to rho. So see, you have integration 0 to a and rho cubed sine phi and sine square phi, I'm going to say, and then d rho d theta d phi. So let's do that antiderivative at this point. So I get 8 times integration 0 to pi over 2, integration 0 to pi over 2, and rho cube will be rho to the power 4 over 4, and sine square phi has nothing to do with this antiderivative, d theta d phi, and then don't forget the limits of rho, these are 0 to a. 0 doesn't contribute, but otherwise you get a to the power 4 over 4, which is a constant, so put it outside. 8a to the power 4 over 4, integration 0 to pi over 2, integration 0 to pi over 2. You have sine of phi d theta. Actually, that should be sine square if I'm not wrong. Yes, that's sine square phi d theta d phi. So I get 2a to the power 4, and now we can do the antiderivative with respect to theta, and I will get theta times sine square phi. Don't forget the limits are between 0 and pi over 2. And finally, you will do the antiderivative with respect to phi. So if you put pi over 2 for theta, that will be a constant which you can pull outside. So it's 2a to the power 2 times pi over 2. Antiderivative 0 to pi over 2. Sine square phi is not simple. You're going to first write it as minus 2 sine square phi over minus 2. Then you will add 1, subtract 1, and then you will have d phi. So 2 and 2 will cancel each other, and you can bring this negative 2 outside, so you get a to the power 4 pi over negative 2, 0 to pi over 2, cosine of 2 pi phi minus 1 d phi. And then I can start taking the antiderivative. So I get minus a to the power 4 pi over 2. Cosine 2 pi is going to give you sine of 2 pi, 2 phi over 2, and minus 1 is going to give you phi, and you will have the limits 0 to pi over 2. So let's put in the pi over 2 for phi. So the first one is going to give me minus a to the power 4 pi over 2 sine of pi, which is 0, so I don't get anything, minus pi over 2, then I put 0, I still get 0, sine of 0 is 0, and I get plus 0. So that's precisely what we will get. So when I take this negative pi over 2 outside, I get positive a to the power 4 pi squared over 4, and which is the mass of this sphere of radius a units. So in this question, we were asked to find the mass of the sphere, and we have found the mass of the sphere of radius a units is going to be given by a squared pi square, a to the power 4 pi squared over 4 units. Answers your question.